He has a master in computer science, which he did here in Saarbrücken and the University of Saarland. He was formerly a CTO of Lengoo, and a head of engineering at Aleph Alpha, where he led teams developing AI solutions and systems. Today, as you can see on the first slide, he runs his own company called 10 Watts, focusing on creating more efficient and scalable AI infrastructure and solutions. He says that he and his company are very interested in helping organizations develop more efficient AI systems. So, Ahmad, again, thank you, and the room is yours. Please, you can start whenever you're ready.
Thank you, Hansa. And hi everyone, nice to meet you all. And I hope that today I can share some interesting insights through my own, at least personal experience. This is just through sort of working with either enterprises or with engineers, helping build efficient AI systems, which I'll talk about why this is interesting and what it means. So I hope I can save you some time and you can learn something today. So for today, basically, as I said, we're going to spend some time understanding, first of all, what is efficiency and why should you care? And then go into the how. What are the different parts that sort of constitute building or designing more efficient AI systems? Important to note, I try to rank this based on, so for most of you, many of you might be building AI systems using closed source API, like just an API. So you might not be doing any data training, data processing to do a training, or just writing your own acceleration engines, etc. So the ranking is based on that. It's not based on importance. And in the end, I want to share just some trends I see, maybe just to orient yourself to maybe like what is coming, and you can sort of prepare your strategy in terms of what you want to implement and how. So what is efficiency? So spoiler, there will be memes, and I will also try to keep it a bit high level so that everyone can understand, and you can go search later if you want to dive deeper. So what is efficiency? So very simply, it's the ratio of a useful output from some system you want to use to the total input. So the total input could be energy, time, effort, basically money, also anything that you want to sort of invest into a system so that you can get some useful output. And examples of this are many in the world. Fuel economy is a common one for cars. If you're having a light bulb, you want to understand how much luminosity it can provide per the wattage or the power consumption. And there's also indices that are developed for many applications using some reference standardized machines. Important to note that it's not always an absolute metric. Efficiency sometimes is actually mostly relative. So our goal is to continuously improve efficiency rather than just to build the absolute efficient system. And as we will see, there's a lot of trade-off involved in that. On the right-hand side, you might have seen this picture before. And so why do we care about efficiency? So there's a general trend in technological progress, and that is that systems, or in general what we're building, tends to become more efficient over time. There's a concept called ephemeralization, which was popularized by Buckminster Fuller, which basically, in this case, it's a bit more funny, says that, eventually technological advancement means we can do more and more with less and less, until we can do everything with nothing. So the general trend is efficiency increases. So we sort of see this as just a natural progression of things. And you see this also, of course, in computers. Since a while, we had data centers that are just the computing that is available for most enterprises and companies, and people thought, okay, this is going to be stuck where it is, and only a few companies will afford that. Spoiler alert, we all have phones in our pockets now that are sometimes even much more powerful than these previous data centers. So this trend of miniaturizing compute is continuing. No reason to believe that it will not stop advancing in that direction. And an important thing I also want to note, efficiency does not necessarily mean we will use less energy overall on the macro level. In fact, there is actually something called Jevons paradox, and as a particular postulate for energy, it's called the Kazum-Brooks postulate. The idea is that even if we do energy efficient systems on a micro level, actually on the macro level, we still use more energy just because the systems are used more. And this was observed by Jevon when he was looking at how basically James Watt's invention of the steam engine led to more coal consumption rather than less, even though it was more efficient. So if you're a system builder, you might want to consider making your systems more efficient, because you can also increase the usage of these systems. And if this is useful, then you provide more value to the world, which is ultimately a good thing. And so basically, that's a good reason for doing this. An important note, just because currently we're in a stage where AI still requires a lot of very large scale compute to sort of run, even for very simple tasks. But that doesn't mean that this is the future. In fact, it's going into much more efficient direction very quickly. And we do expect that hopefully this continues. Not only because just the trend continues, but now we also have AI that helps us build better systems that we can then use to build better AI. So we're, in some sense, have a circular sort of feedback loop, which is very useful for us to make the systems more efficient. Okay, so finally, I want to summarize this, that more efficient AI means we will have them more running in more devices, in more locations, and ideally running exactly where the input data is provided. So where we sense data and where we get feedback so that the models can improve over time. And the more these systems are available, the easier it is to access them, the more they will be used. So there's a saying in photography that the best camera is the one you have with you. So if you have AI easily accessible, when you don't need as much like an account and money and an internet connection, this makes it easier for you to use. Privacy is, of course, a big topic. It will hopefully integrate more into our software. Like we run, all of us today, software on our computers that run locally. Like if we're doing video or photo editing, for example, if AI is just integrated in it instead of calling an API, that makes them also much more easier to use and like it reduces latency, for example. And then, ultimately also, if we have AI systems that can run and harness energy from their own environment, they can run indefinitely and can run almost independently, which is hopefully a good thing, despite the matrix warnings. But of course, we have to do this safely and conservatively. But this is also something that will make AI more useful for all of us. So how do we do that? How do we go about building efficient AI systems? So as I said, this is sort of my experience based on different parts and where most people tend to spend time versus less. And of course, it all starts with how you design and think about the system that you want to build. Basically, an AI system that you are designing needs to answer two questions. What is it supposed to do? What is its objective for existing? And how is it existing in the world? How will it achieve this? In other words, basically, what are the constraints it's working with? So the environment usually sets some constraints on how basically the agent or the AI that you're building achieves its objective. If we actually can avoid using an AI and build something with software, it's actually more efficient. So we don't always need to use AI, but assuming we use AI, that's where we're continuing. And the constraints tend to be many things. It could be that latency is the most important constraint you have, or cost, or privacy, or accuracy. Sometimes you have actually resources that you can leverage. So you say, okay, I have a lot of compute. I just bought a lot of GPUs. At some point in time, I might as well use them. And then you use AI. So sometimes it's not just that you have constraints, you can also have resources that are available that you can use. You have expertise on your team. People have built AIs before that you can leverage to build more AI systems for you and maintain them, because maintaining them is also an expensive thing to do. So once you have answered these questions for yourself and you know that you need to use AI with some particular constraints and trade-offs, examples of how that could look like can be very different in startups versus large enterprises. So let's take something like you want to optimize latency. You start looking into smaller or quantized models, but then you find out that maybe the accuracy is not enough. And then you start saying, okay, maybe I'll then invest in more GPUs, but the cost might be prohibitive. Similarly, you start thinking about maybe fine-tuning a smaller model, and then it becomes more efficient, which we'll touch on a bit later. But then you realize you need more data preparation and expertise, so etc. You see the same thing with cost. So overall, you need to have clear priority on what your constraints and resources are, so that you can make these trade-offs. It's sort of a bit unavoidable, at least in this moment in time, where just AI systems can be a bit more expensive for some expensive, or also add in slow for many applications. It's actually a big topic also. How can we make this scalable? So overall, you have to make these decisions and understand a bit what your system is. And sometimes the success of the system is not dependent on the availability of the technology. It's actually about your own business priority. So that's important to have some good decisions there before we get started. But what can you do also a bit more practically? So when it comes to input, so if you have a problem and you want to model your input, so you use an AI to sort of process this input, there's a few sort of rules of thumb you can think about, and you can think about it in the following dimension. So if you have a task that is very specific versus generic, this is sort of one dimension. A generic task that sort of needs a lot of domain knowledge and world knowledge tends to require bigger models. Similarly, if you have a text only versus a multimodal input, like you have images plus text plus maybe even audio or video, then of course the multimodal requires more computation capacity, and it's larger models, so can be less efficient. And single language versus multilingual. So basically, the more dimensions your input has, the more expensive your computation will be. So if you can find a way to narrow down your task, as in like you can convert some of these things, for example, from images to text, or similarly just make the domain more specific, you can make your models much more efficient. Again, just because you need to process less input. On the right-hand side, you can see like this kind of gradient of like going from like very simple, you just want to have text and you classify it like good or bad, or like sentiment positive or negative, and going to maximum input where you need a multimodal, multilingual, multitask generic system. Of course, you will need a much more generic large-scale systems to do most tasks reasonably well. This is, of course, assuming you have done a lot of other optimizations in relation to like not using too long prompts and trying fine-tuning if needed. And for the output, it's even more important that the narrowing of the domain happens, because it tends to be that having different output types consumes much more capacity than processing multiple input types. So if you can make the output type, for example, instead of trying to generate images from the model, you can use a tool for that, tends to be more efficient. In fact, this may be one of the reasons you tend to see the like video or image models separate from just normal models. Some of it is technological also, but capacity is an important part. So if you can have like a large funnel to a narrower funnel, that tends to actually be more efficient. And you can actually get away with processing a lot of different types of input more than producing a lot of different types of output. So if you can narrow down the output, it's actually even more important, I would say. Important thing to note, the large models tend to anyway have diminishing returns if you narrow down the task, so you can also get away with using a smaller model, which is ultimately makes you a bit more efficient. And interesting also to note that the end game, we still think, is going to be these multimodal, continuously learning systems that are learning on device even. This is just too expensive at this point in time. So if you do not need that, and if you can tolerate also errors from transforming between modalities, like converting again an audio to text first, sometimes again some information is lost during this conversion. If you can afford to do that, then this is the way to go. But hopefully in the end, I think probably the trend will be more native multimodal inputs, and we use tools for our multimodal outputs. So that's how to think about sort of when you're designing a problem, how can we narrow it down so that we process enough input for our task and produce an amount of output that is reasonable for the task and not too much, so that the model doesn't need to figure out multiple times of output at the same time. So assuming now we want to maybe train a model or use some data for retrieval or in-context learning, how do we do that? So generally speaking, the data topic is something most of us will spend a lot of time with. In fact, I think, as you know, there's a lot of tech companies that basically data is what defined their value, their IP, user data, code bases, experiments, the attention they hold from this, we're living in an attention economy, etc. I think as AI does more and more tasks, the data part will become even more important, and most companies will transition to being data companies if they're not already. And that means advice from any company or any person sort of working in doing any investments in data organization, like making your data a bit more easily processable, is going to be a very wise investment to make, regardless of whether you use AI or not, or which type of AI. That kind of is the thing that will pay dividends later on as the technology also progresses. Someone on the internet made this meme, because I agree more. So that's just an important thing to note. Investments in data tend to pay off very quickly. So that's a good investment to make. Now, when it comes to thinking about AI, when it comes to data, basically AI is a data processing engine. So your data I/O is what defines what you're doing. And actually, in my also personal experience, most of the issues people encounter are in the data sets they use to either train the model or use them for in-context learning, as we mentioned earlier. So spending effort on processing, curating data, which we'll talk about very soon, is what we'll probably most of us spend a lot of time on as engineers, just to make sure that we get the most out of the system. We'll come back later to why the modeling part plus the inference and optimization on the other side are less relevant, mostly because all of these things can be done like across the board for many people to reuse. This is specific to each problem. A very interesting paper I wanted to reference here on the side related to adversarial input that models face and tend to produce a very different output, or sometimes called hallucinations. Models are very good at finding sort of irrelevant patterns, to us at least, that are very relevant for the task they're doing. So building robust data sets, which are usually like just clean and relevant, is something that also improves the accuracy in general, regardless of efficiency. So it's important to focus on this topic. So how do we do that? My favorite topic is actually data filtering, which is funny because it's sort of like not focused completely on AI, but in my experience, this was the biggest bang for sort of time spent on getting AI systems to be better or more efficient. Just basically helping the model remove irrelevant or noisy data through filtering, which is very common also in pre-training, means your model has more signal, has more capacity to focus on your signal. So sort of like a person, if you remove a lot of noise, they can focus a bit more and achieve more output with less time and effort. Similarly for the model, if you don't sort of give them a lot of patterns that they try to figure out that they are useless, so this is what they will spend their capacity on, you can do this ahead of time and you can sort of save the effort for the model to figure this out. You can get away with a much smaller model because the patterns that remain are much smaller. So yeah, at the end of the day, what issues you might face if you have data that does not conform to a particular format that you are supposed to have in the data set. So some of it is parsed wrongly. That's something that the model will need to figure out sometimes because the parsing has a consistent pattern. So it's an incorrect pattern that your model can learn. Anything that is an outlier that tends to not occur in production. So if you have studying your data set in terms of finding outliers would be interesting, like something that is very short or very long. If it's like sentences, something that just has a very different vocabulary, etc. So unless you intentionally want to add it there for robustness, because you might face this in production. So that's why the production part is important. And other than that, also to not let your model, again, learn things like XML parsing or coding if it's not in your task. So it's expensive to get the model to learn to do JSON parsing if you can just put a parser ahead of time. And yeah, anything that is invalid, empty sentences, corrupt encoding can be fixed also, but if it's not in the data, the model doesn't need to be confused. Again, some of these things could really hurt the performance, even a very small percentage of it. It's really fascinating to me sometimes how removing a very small amount of noisy data can lead to a big jump in performance, even though like the data amount that was removed was very small to us, like okay, 1 or 2 examples, but they can really be harmful to the gradient sort of learning of the model. And then, yeah, finally, just incorrect data, which is very common. If the data looks correct and has all the proper formatting and everything, it's just that it could be incorrect. It was labeled incorrectly. It's not the outcome that you would want. A lot of time, this is human error. That's also something worth investing in fixing. So once you do that, you will find that actually even smaller models can be quite effective. An example of that is actually a lot of newer, more sort of modern pre-trained models spend a lot of time on the data cleaning. This is from the Fine Web. There's a Fine Web 2 now, but you can see that, again, with just adding more filter, as in removing more data, you can get better performance. So that's something that sounds very appealing to anyone seeking efficiency. You can sort of remove stuff, compute less, and get better performance. And some of these examples here are rule-based, like you just remove incomplete sentences. Sometimes the check is related to punctuation at the end. Not always works, so you have to find out whether this is, sometimes you want that actually this is your data set. So it's not just the generic patterns, but that's why it's important to look at your data set and spend a lot of time understanding what it is that is desirable versus not. And similarly, other than code rule-based sort of hard written rules, you can also use models for that. So if you have a data set where you have good examples and you have a data set where like you want to remove some bad examples, you can sort of get a smaller model or a model that you just already have and learn what are the patterns there. Maybe it's perplexity, because sometimes like just very noisy text has very high perplexity. It just doesn't exist in real data. And you can then filter based on that. And yeah, in general, you can spend a lot of time finding out which labels or mislabels your data set tends to contain. It's a bit different from different data sets. It's more relevant to the task you're doing. So effort spent there, again, is worth it. If you sort of have that and you clean your data and your problem now is no longer noisy data, but actually too little data, then the next stage is basically to make more data. Crawling is usually a good idea because you capture real life, real world data set and you don't have to build it. That's usually cheap. If you don't have that, then get or hire human labelers. A lot of companies have internal people that maybe produce the original data set or something that they want to produce. They can get examples internally. So if you can do that, then that's the second best thing. If you cannot do that and you have maybe output, but you don't have the input, then you can generate the input synthetically. That tends to also be good if the output is of high quality. if you have such data that you want to make more of it, you can do variants. This is very common computer vision, where you flip images and change their orientation and do a few other things to just get them to give you more variants. And then finally, distillation. Distillation is basically you generate an output from the model rather than an input. It tends to work well for making models more efficient, so it's actually quite recommended. But it's, I would say, like the downside sometimes is that if you don't do distillation well or with a good model, or you need to do this on a very large scale, you can introduce actually more noise because you're teaching the model AI output rather than human output. Usually, our goal is to produce as much as possible human quality output, and that's expensive, but distillation tends to still work quite well if we want to optimize. And in fact, it's very commonly used as the main way to make models smaller. And that's basically just training the smaller model on the big model output. And I think the reason that is a hypothesis, I think maybe someone can prove this or prove this at some point, is that distillation is in some form of data cleaning. You're smoothing out the curve of the data set by using a model that has sort of already done this smoothing out by its own learning process. So through doing that, you get sort of more efficient data sets by just generating them. And then finally, once you have a clean, augmented large data set, you split it. And I would say for evaluation, which is a very important topic, of course, I just want to touch on it because it's not necessarily like an efficient related topic, but of course, if you evaluate well, you get there fastest, which saves you time. That's also efficient. Eventually, if you can test in production, you can do beta testing, A/B testing, have humans in the loop, and then shadow what they do versus what your model performs, so you can get a good signal of whether this model actually works or not. All of this is very useful, but of course, before that, you need to build a robust benchmark. It's a very underestimated task, or underrated also. So both, it's like very valuable and not easy. And in fact, the more we focus on that, the more we can do that, the faster, hopefully, we can solve our AI problems. But again, we need to get a good amount of data that is somewhat diverse, has a good coverage, stratified, so that there's not like one label covering most of the data, or one class and most of the other classes have very little to no representation. So we have a skewed evaluation. And finding good metric suite that fits our task is also an important topic. So yeah, and just to put this message again, I cannot emphasize this enough. Spend enough time looking at your data sets. You will find very surprising things. And real life or real world data sets are just full of spurious correlations. So the more natural, the more clean, the more parsed your data is, the better your models are going to be, but without too much capacity. This way it's on just figuring out the noise. Okay, so if you have now a good data set, and this is still not efficient enough, you still have problems with your application or what you're building, then we start looking, okay, how can we make the software and hardware parts faster? So as a rule of thumb, if your application is the bottleneck, then you need to do some work. Ideally, at the end of the day, your GPU is the bottleneck. So you don't have enough compute. If you don't have enough compute, then that's not a bad problem to have, because over time, GPUs get cheaper, they get faster, and you can get hopefully more of them if your application is sort of financially lucrative enough. Even applications like ChatGPT, when it first started, nobody anticipated the demand, and they had to figure out how to do GPUs. Till today, this is the case. But if you don't know that you have a need for that, then you don't need to start optimizing. And similarly for the application. But if you start finding that your application is actually the bottleneck, not the GPUs, then try to see if you can iterate with some dummy data sets and try to get to a point where you can process thousands, tens of thousands of requests or more, depending on what kind of task you're doing, without the hardware part, without the GPU being there. And this is just software, so just be doing data structure algorithms, multi-threading, caching, use faster libraries. Eventually, you could go down the route of rewriting your code. A lot of AI backends are actually Rust or in Go, or sometimes in C++, actually a lot of times in C++. On the right-hand side, you can see this famous table about programming language efficiency. So it's a good way to start thinking about what you can use and write. Of course, you have to consider portability, that you can actually maintain it in-house, all of these things. But if you can get to a point where the bottleneck of whatever you're doing, whatever the application is not your actual code that you wrote, but really the GPU and the inference engines plus all the firmware on top, that's a good place to be. Then you've done your job. We can switch on to the next thing. So that's a very important part. If the application is fast. A big part of that, of getting more value out of your existing hardware, is batching. So a lot of people, I've seen this many times, a lot of people are not batching their requests, as in like sending multiple requests at the same time to a GPU. GPUs actually are much better when you batch more than just sequence. Like they're also fast, like in a single request, but the biggest advantage by far is batching. So if you want to maximize the utilization of your GPU, you would need to batch. In fact, the bottleneck of GPU performance is more memory, fetching data and putting it back and forth, rather than the actual computation. So batching cannot be underestimated. It's really something where you can just optimize throughput mostly, but you can optimize your performance without having to get new hardware or increase costs. Because if you have a GPU, you have that GPU already, might as well utilize it as much as possible. And luckily for us, a lot of inference engines already implement a lot of optimization, so you don't have to because batching also you can, for example, if you have a lot of short sentences and long segments, long sentences, and you batch them together, there's a bit of wasted computation because they're all sort of batched in like one matrix. So you need to generate this differently. But a lot of inference engines such as VLM do continuous batching. So basically they can process things and add them and remove them when they're finished. If something is short and finished earlier, then it can replace them. So all of these things are done. But if you're not doing batching, not sending things in batch, then this is usually a bottleneck on you. So first you have to figure this out and then leverage what exists already to improve it. On the right-hand side, you have a famous meme. The person has nothing to do with that, making GPUs go burr. So first make the GPU go burr, and then if that's the problem, you have if you still need to process billions of requests, then the one GPU is not going to be the problem, because even if you process requests per second, you will still need a lot of GPUs. So in this case, you start thinking about, okay, I upgrade to a better, bigger GPU, so you can do more batches at the same time, or you can have more GPUs. Usually, getting a better GPU can be a bit better because you have more memory and faster memory. But this depends on your problem, so you can look into that, of course, what kind of hardware budgets you have and what hardware you have already. So look into that, and if you really have a need for it, you can look into more efficient hardware, like TPUs. Neural engines are now also quite popular in most applications if you run something on edge or on laptops or smartphones. There's even now more specialized hardware coming up, so you might need to find if the hardware is the bottleneck and you have constraints on your energy, your just power requirements, then you can look into that as well. So sometimes again, we do all of this, but it's the hardware still the limitation rather than everything optimized before. So then you can spend more money. Okay, so let's say you've done all of this and you still want to think about more optimizations and you need more efficiency. Then you start thinking about model architecture. So spoiler, to be honest, I would say for most of us here, there's a reason why we're converging all on the transformer, and particularly even a decoder version. It's just there's a concept which I like, it's called a hardware lottery, is that over time, actually, some particular research ideas win just because they fit the hardware. I think also sometimes the hardware fits to the research idea that wins, so you end up with this feedback loop. So a lot of software and hardware and firmware is being more optimized for transformers and variants, like even particular ones like Llama. So if you want to invest in going that route and saying, okay, I want to do some changes, you have to realize that this is an expensive thing to pay for, because you will have to also invest in optimizing the inference stacks behind it. You have to invest in making the rest of the patching, everything like this, work also a bit more efficiently. So do not do this if this is something that you need to do, because sometimes actually, even if you go that route to make something slightly more efficient, like 1 to 5%, the gains could be completely sort of lost if the next version of something comes and everything is optimized for it. It will end up being less efficient anyway. So sometimes just moving with the wave is actually the wise thing to do here, and not having to either reinvent or tweak things. So even not using an LLM at all could be an option. So if you realize actually your problem or data set there's a lot of applications now that still do not use necessarily a transformer or LLM. This is not like the one all be all solution, because again, speed is a big bottleneck for a lot of these applications. Then you have to think about different things. You can still use deep learning. Maybe you can create your own hashed features. I think the TikTok algorithm from the paper Monolith is using some form of that. I would recommend to check it out. It's a very nice paper. And in general, you go to transformers if you need more nuanced language understanding, or just patterns that are a bit more not possible with just hashed features that or features in general that put into a machine learning model. So yeah, if your data set and model compression ends up being much easier actually than you originally anticipated, there's no shame in going to an even smaller or simpler algorithm. That if that makes your accuracy sufficient and you're able to scale, then it's perfectly fine. And again, I've seen a lot of production workloads which use very simple systems, and they work much better than if you try to just put an LLM or develop an agent for it. And if you then want to use a transformer architecture, it seems that we're converging also more like to encoder only for just embedding related tasks, and decoder only. So even encoder-decoder models are falling a bit less out of fashion, which were some of the first models actually used. So again, just a lot of it is mainly also due to more optimized hardware, firmware, software on top of it. So going that route is the recommended way. If you need to have further optimization, you can start looking at mixture of expert encoder-decoder models and things where you have like some parameters that are loaded. There's not like the new ZeMA 3N. It's actually quite a good example of that. I use this picture here, where you can preload some of the parameters or not based on what you need. That's also something you can look into. If you need some, like let's say you do a task, sometimes you have an image, sometimes you don't. That could be an example of that. Okay, so now we have hopefully figured out a good scalable architecture. We figured out all of the pieces related to the code that we are building, the application or the product. Now we can think about, okay, we can optimize the training or the inference a bit further. And this is where we can think of a few things. One is using so-called adapters or quantization. And the other is understanding newer trends like bit transformers and work that is going towards like making the whole resolution of the models much less. I mean, these are all sort of somewhat similar ideas. For the most part, if you have not a very large data set and you don't have a very challenging task, you can get away with, again, much smaller models. Basically, you can scale your data set as your model as your data set scales. And for most part, most people will be fine with just out of the box fine-tuning setups, because usually if you're finding on a small data set, the efficiency, you do this 1 or 2 times, you're not doing this like necessarily every day. If this is the case, then you would need to optimize the training part as well. But for the most part, you will just use existing systems. I saw this today, actually, on the right-hand side, Shopify use case where they used the Llama 2 7B for a task, which was in this case, they wanted to produce some information from a product image to help their people on the with their shop, basically, on Shopify. And they could not do this at scale with the closed source API, just because it would be too expensive. And they also tried larger models, so it's a bit expensive. I recommend to read this use case. It's just a very good example. I was actually very happy to read this because like, a lot of the things I was talking about was more or less covered there. So you can see that even very high scale, high volume production workloads can be done very well with, again, focused small models that have very high efficiency. So at scale, this is pretty much feasible. And you do some fine tuning and your data set, you spend some time on that and you'll get a good outcome. So if training is no longer a concern, then maybe look at inference. Luckily for us, very much luckily for us, because this was not the case earlier. I remember the days where you had to spend some time on optimizations for your own hardware. Luckily for us, we have now most hardware supported by inference engines. You can run things on ARM, you can run them on Macs, you can run them on phones, you can run them on different types of GPUs, both AMD and NVIDIA. And a lot of because this is one thing maybe not a lot of people know, but actually to run these models very efficiently, there is a lot of work on the back end, optimizing on assembly level, basically, to get these batches of computations to happen very quickly. So it's not just works out of the box. So a lot of this is actually handwritten by Peter, and many companies do invest in that as well to optimize it for their own custom needs if they have a special implementation of a transformer or something similar. Luckily, again, these things can be reusable, so we don't all have to write it and rewrite it. So that's one thing. Use that as much as possible. Use it for inspiration if you need to write your own kernels, CUDA kernels, or assembly intrinsics. I would also recommend to look into how to run multiple LoRa models if you need to scale to run multiple of these models into platforms that do this for you. This also means you save a lot of costs. And in general, things like quantization tend to work well if if that's your problem, it's somehow also still better to use full resolution models, but quantization works much better than when I remembered using it for the first time, I think 5-6 years ago. And you get a lot of basically features also out of the box for free. So we're in a much better time than before. If you worked the early sort of days in NLP, 2018, 2019, where there was very little tooling, now basically it's sort of much easier to reuse than to build stuff yourself. And more of these things are, again, just available as open source, so you can reuse them as needed. And the materials, people are generously sharing them, so you can also reuse that as well. But the important thing to note is that you don't really need to implement a lot of these optimizations, and do not underestimate how much time this takes. So look into if you use something and it works fast enough and it's optimized, probably better off using it also out of the box. So thankfully, this is available to us. Okay, so hopefully this provided you with some like clear guidelines and direction how to start and where to look. Where sort of is my personal view on how trends are going into sort of more efficient AIs. So yeah, that's what I want to share now. So one pattern we tend to see, I mean, historically speaking also, you have more basically or tighter vertical integration of the hardware. So the hardware tends to be more squashed. So we had these large tubes become transistors, the transistor becomes even smaller by MOSFETs, which then become an integrated circuit that's printed. So it's actually not as modular as we would like to have, because a lot of us for engineers were taught to think in modularity, but actually a lot of it is just squashed into much more complex design systems. And you can also see this in CPUs. We went very quickly in the last few years, maybe a decade, from just separate microprocessor and microcontrollers to systems on a chip. And there's no reason to think this will not change, as again, more breakthroughs in either just manufacturing techniques or just designing these chips. Again, specialized hardware is all example of that. So we will probably see even more hardware specialized for AI. We will also see these hardwares very tightly integrated with the firmware. Again, as I mentioned, there's a surprising amount of innovation and work happening actually on that level. In fact, you can actually think of deep learning progression as optimizing for hardware. So AlexNet using CUDA is not a deep learning breakthrough as much as how it is that we train this model with the hardware we have. So the ideas of backpropagation and sort of training existed since a long time, but we have the hardware to do it, and we have now some people skilled enough to also use this hardware well. Similarly, all of these things, even the transformer architecture, was sort of to maximize the parallelization of training these models as compared to RMNs. A lot of the even newer things like KV caching and flash attention are, again, just very much hardware-aware, low-level programming things. So we're going to see more of this happening. There's even companies literally burning the transformer architecture into chips. Again, all this increases sort of efficiency. And if you remember, as I mentioned earlier, the memory is a bottleneck. If you sort of hardwire things, you sort of can end up with less memory. We're seeing this more just in the trends of how computing is moving. And yeah, finally, we also expect to see more AI-first products, as in that the product is sort of the AI itself, like ChatGPT is a good example of that. It's an AI, you're just literally talking to an AI, and that's your product. And more of this is things like, again, lovable, things like, more of the applications that basically just you interact with to build stuff rather than building it and moving it yourself. Although I think we will still have, like, people still like to do things with their hands. People, I think, will still want tools where they are much more in the driver's seat. But tools where the AI is basically the companion and you're sort of asking it to do things for you will become more available, especially as we move more into the real world and have sort of interactive AI, which I think is going to be a big next topic. This is, I think, now at this point everyone talks about this. The reason for that is we want AI to be closer to where information is happening for privacy reasons, but also for faster learning, for more efficient learning. Again, going back to like the Jevons paradox, the more sort of efficient on a local micro scale, the more hopefully we can use it on a macro scale. And important to note, adoption takes time. We have technologies that have been around for a very long time, like email, but we still use letters and we still send post. So it's just because something exists and state of the art doesn't mean that everyone will adopt it. That takes time. Hopefully making it more efficient, more reliable will increase the speed of adoption. And that's hopefully where all of us can contribute. And if we can get to a point where we have an AI that's continuously interacting and learning in real time, runs multimodally, multilingually, all on a very hardware or energy efficient hardware, such that it can power itself, hopefully by solar even, that means we get AI that's somewhat independent. All living creatures sort of need to find food and continue to exist on their own. AI is sort of still very much dependent on humans. So if you want AI to be more useful, hopefully it can also be more independent. Again, hopefully without too much of the dangers, and developing it safely and responsibly, I think, will be something all of us have to focus on. But getting to these kinds of products is hopefully going to be a place where, yeah, all of us can use much more AI. And that's it. I hope it was useful. Thank you for listening.
Well, for me at least, that was extremely useful. Thank you very much for this insightful talk. And
Thank you.
I think we would have an interesting discussion here. And I know already somebody who was eager to ask the first question. And he happens to be also an AI expert. Teresa, can you please unmute Omar?
Hi, do you guys hear me?
Yes, we do.
All right. Well, I must say the talk is very interesting, and it not only reminded me of some of the things that I usually in my work I forgot about, but basically the stress on data was was basically a good reminder of of the process that I go through during the work I do, and it's a very nice talk in general. I actually wanted to ask one question, just like a general vision question somehow. Do you see, I mean, based on on your experience, people going the route of fine tuning more, or do you think people are just depending on calling external APIs like OpenAI or I don't know Anthropic or whatever? Because in my line of work, at least, that's what I noticed, is that in order to fine tune something, usually you need to, or if you want to host some model on your AWS environment or some cloud environment or something like that, it's usually very, very expensive. Even for a 7B model, it can cost you about thousands in a month. Yeah? And for any like a startup that wants to do some fine tuning, that's a lot of costs if you think about it. Yeah. And and in my mind, OpenAI and all those big systems, they just basically benefit from the fact that their systems are busy all the time. That's how they can justify the cost in general. And I would say that I've been working, let's say, for my last job, let's see now about 3.5 or 4 months now, and I never seen somebody fine tune something. Although we have lots of cases where fine tuning would be very, very beneficial. So I'm not sure. What do you think? I mean, do people actually focus more now on fine tuning, or do they leave it out to the big models to handle lots of use cases that can be fine tuned? Yeah.
So thank you for the question. It's a very interesting, very important question, and I get this question a lot. So I don't think it's sort of like going to be if or like you only fine tune or you only use big models. I do think you will have both. I think we will need both. We'll need large models that have very sort of good world knowledge and can solve these problems where we actually don't even know where to start looking. And I think these large scale generic models are going to be very good for that. But so for example, the thing I shared earlier about Shopify using a smaller 7B model and deploying it, if you have the volume for it, and that's a very, very important part, if you have the volume to keep this model busy, you can also like turn it on and off. You can do sort of auto scaling if the cost, because just keeping it running idle is very expensive. That's something that nobody should hopefully do. But if you can keep it busy and you can sort of put it on, patch, process your requests, and then turn it off, that then becomes a very viable and very feasible thing for most startups and companies. If this is your main product and it really adds value, you would need to see, okay, like how much money will this make compared to its cost? So it's a business equation at the end. But the way I see it, I find that like if your main product is AI, or you do something where AI is at the center of your offering, hosting it yourself tends to eventually pay off if you have a lot of requests, also for the bottom line. But if you don't have that and the scale is not there, using a closed source or API is actually the smart way to go until there's enough demand where this becomes the bottleneck. So there's no reason why to not start somewhere and then eventually transition into using a fine-tuned on-premise. There is also reason to do this with an API. There's APIs that offer fine-tuning, so this is not like, again, something that is you also only use an online generic model. You can do fine-tunings also in OpenAI and other tools. And the reason for that is also to optimize either your prompt length, so instead of prompting every time and getting sort of an outcome, you can reduce that time by fine-tuning. You can also get away again with more efficient models that already exist there. So there's a lot of reasons to also use fine-tuning even with an API.
Yeah, and I think in general, yeah, that's basically how also I kind of think about it. And that there is one thing happened recently is that I'm working mainly with AWS, and one thing happened recently is that they have AWS Bedrock, which is now getting more and more popular, and they just introduced a feature called custom model import, which you can basically use to scale in and out your models basically. So whenever you get no requests, you have no instance or you have no GPU running your model, yeah, which was not before the case, yeah. So it just happened, I think, a month ago or something like that. So that is a good thing, and I think lots of people on AWS are going to use that. But the stuff that you talked about fine tuning models with using let's say an API like OpenAI or something, I think most companies will be concerned about data safety or their data going to OpenAI basically, and they don't know what is going on with them or whatever they want to do with this data. So I saw it in the case before where we actually wanted to do that, but we were afraid basically, and the legal team just kind of give us all kind of problems with legality of this, and I don't know, the data that's going to OpenAI and stuff like that. So it was a really big problem. But I think there are going to be solutions in the future, I think, for this particular one.
Maybe. Yeah, that's why, as I mentioned at the beginning, that it's very important when you design the system to see what are the biggest constraints. Privacy is a big one. That's like sort of the top 10. So you already know you maybe cannot use as much any kind of APIs, even if this is the more efficient route, just because you have the constraints of just privacy. So it's really important to think about these things at the beginning, because there is multiple ways to go about efficient systems, or like building things fast and cheap and efficient. But it's all about first realizing which environment you work in and what are the biggest constraints.
Thank you very much.
Thank you.
Thank you, Ahmad. Do we have any other questions from the audience or from YouTube? I see nothing here. Teresa, anything on YouTube? Okay. So then I have a question for you, and it's probably more related to the activity of your new company. So from your experience over the years, what are the most common mistakes that companies tend to do while trying using AI systems?
Can you repeat again? What are the
mistakes that companies, mainly, I don't know if you worked with small, medium enterprises before, because that's a big topic for us. And that is also valid for bigger industries who are probably a little bit less open to such solutions. What mistakes do these companies tend to do? Or also, it would be also interesting to know how flexible or open are they to using such systems in general?
Yeah. So I would say, so the mistakes are probably different based on who you ask in the company. But if we're talking more on the engineering side, probably most of the time is over engineering. I would say is more common. That's like what I see more. It's as in thinking about using either over optimizing too early, or not thinking about like gradual going from, again, what is the minimum set of either tools, models, thing we can do to get a very good outcome, and then scaling from there, because that like time is really important for especially smaller, medium companies. It's sort of the biggest asset of most smaller companies. So being able to be fast is sort of or like setting off time and not being fast is the biggest mistake I tend to see. Probably not batching. Not enough companies are batching. I think a lot of people sometimes there is a fear of sort of like, okay, I don't understand AI, I'll just try something very easy locally, and then you see that it works, and then you assume it will scale. But yeah, understanding that batching is a very big part of AI workloads and trying to design your application to do batching well. I think these are all kinds of things that I tend to see more. And then I actually am on the camp of thinking like people who come from software background can pick up ML faster than ML can. People can pick up software. So I actually think there's a lot of advantage to people who are in software to use the skills they already have and just get more into ML and not be intimidated. And actually, I think sometimes that is the problem. I see that more people coming from software are a bit intimidated by ML and sort of feel like, I don't really understand it, so I don't really like it, or I don't want to use it. But yeah, just if that part is sort of overcome, I think they tend to build very good solutions, because fundamentally, I think it's still a software tool in our toolbox. So just think of it this way: will make people's lives easier to just not worry about relearning completely from scratch everything. It's really just more using the models as they are and trying to narrow down a bit your tasks and be, again, more accurate with your prioritization requirements, etc. So.
One more thing you mentioned earlier at the beginning of the talk, that in some cases using AI is not the efficient thing to do. Did it happen to you that you faced a case where you had to tell the company or the client or whoever that they should not use AI and use something conventional instead?
It happened more, to be honest, with problems I was solving, but I'd say with customers, yeah, maybe I've seen more people overuse AI than not. So, for example, instead of, again, just parsing something with a parser that already exists, using an AI to do it, or like providing this as input directly to the AI, which actually might be efficient for some use cases. If, again, you have very low requests and you don't want to spend time writing the code to do that, just send it to a model and figure it out. And as the model gets better, it will solve it. But for many use cases where like sort of the data part, especially, I've just seen people maybe overuse AI instead of just doing a bit of the pre-processing at a time. Which, again, if people have read here the bitter lesson, it's more advisable to think about turning software problems into sort of AI problems. Is a very good advice to sort of do that. But again, if that's not the bottleneck, and you can focus on getting a just faster outcome from the existing setup you have, you don't need to use AI for everything. And yeah, I just seen this also. A lot of the time, it's more for classification. For a lot of classification problems, you can use an AI model, like a GPT kind of model. But for many cases, a very simple classifier with something like fast text or just hashed systems, again, just like we've seen with the TikTok, for example. I know it's still the same thing they're using since they published the paper. But as you scale the system, it tends to not work anymore. So for probably very high volume applications, we start to see less actually large models and more either small model or no models. That's actually a bottleneck probably to adoption, and that's why I think this topic of efficient systems is going to continue for a while.
I have one last question, which is not very technical, and that is, do you have any fears of the fast evolutions of today's technology? And if you have, would you like to share them with us?
So I'm an optimist.
Not fears, but maybe concerns.
So I'm in general an optimist. I tend to think things will turn out better than we expect, hopefully. That doesn't mean we should not put in effort. I think, as in like to address some of the concerns. Of course, I don't think the energy topic is a concern. I actually think the concern is probably that we're not generating enough energy in the world. I think we will need to generate and use more energy as we sort of develop. And the world is full of places where there's still like people don't have refrigerators even. So we will need to use more energy. So I think if we develop efficient systems, I think that will help with make it cheaper for people to adopt and use the technologies. So the concern I have is just a widening gap of like, okay, you can afford to use AI and nobody else can afford because it's too expensive, which I think is not going to be the case, again, just because the trends I think is naturally going to continue. So that would be one thing, because AI is going to be very important for most applications. In fact, just like the internet has changed lives of people, I think the internet will do this even more so. The AI technology sort of shift we're seeing will do this even more so. Like people who have computers are much better also off than if they don't. So that's the kind of things where I hope we will see more people be able to access and use these technologies, and hopefully get access to also like the state-of-the-art best models. And that should not be. We're already seeing this in the political landscape, where like some countries should get some hardware or not. So I hope that this is not going to become a big topic, and sort of there's going to be a bigger gap. Some countries will have the best AI and some will not. But I think also maybe it's a good wake-up call for everyone to invest a bit early in their sovereign AI strategy and figure out how to do this, so that they're not left behind. But yeah, that would be the main thing. I think there is also, of course, the concern about AI safety, which is, I think, addressed. The reason I didn't talk about it as much is because just I think it's a very big discussion already happening. I still think it's very important. I see the role of it more on sort of people developing these systems and making it more accessible, rather than just completely reinventing what we're doing. Like I do think we are on not such a bad track. And I think most people working in these systems are responsible enough, even though sometimes people say, okay, you're not responsible enough. I feel much more concerned about this. I think we can be all reasonable, and we all should think of each other as like we're all not trying to mess up humanity. I think that's hopefully a good place to start. And from that assumption, we try to see what we can do. So,
I see how optimistic you are. I have a few questions from the audience. I'll read them from the chat. And the first question is, from your experience, do companies and people in the field of AI rely more on hardware acceleration rather than software acceleration, and not paying enough attention to app acceleration?
Yeah, I do actually think that is, I think, the case. So a lot of people, again, just at least I've seen more people than not, because a lot of people are not working on the hardware acceleration level. So that's why not a lot of people are paying attention to that, trying to maximize the GPU and not like thinking one level deeper and forgetting what their part is in the software part. So I would say, because the hardware part is sort of hard enough that people don't. I mean, I do think there's not much also to do in the hardware part. So I think people should pay attention more to the software part that they're doing, or like the application part that they're doing. So I think this is definitely the case, but maybe not because they're not paying attention to like enough the software. It's just maybe just they're not paying attention in general. They're just like building something and it works. And it's not, I think, from paying too much attention to the hardware part. And when people have money, I guess, to spend, then the hardware part is easier to spend money on and just accelerate. Because again, you don't have to code the hardware, you just buy the hardware, so it's a money problem. While the software, you have to change it, you have to write it. Although with AI now, we should be able to write hopefully more efficient software, easier and cheaper. So it shouldn't be a problem to do that. But hopefully more people can. That's also one of the things I wanted to highlight here, that a lot of the work we can do is still on the software side for most people at least.
Well, I think we don't have any further questions. People from the audience are already texting thank you messages. So again, Ahmad, thank you very much for taking the time and being with us this afternoon. It was a really pleasant talk and discussion. Good luck with your new company. Maybe we could collaborate at some point. And thank you very much.
Thank you, Hansa, and thank you everyone for listening in. Hopefully this was useful, and see you around. Build great systems.
Thank you.
Bye. Thank you.
Bye-bye.